Good morning, all of you. From Professor Rupinder Singh. This is NITTR Chandigarh. Uh, we are here for the discussion on some advancement in 4D printing with special application for maintenance and repair of heritage structures. I'm really thankful to Dr. Khalid for this opportunity and have a august audience with which we can have a lot of interaction and can work in this area. Specifically, I have put the target for using this 4D printing in the maintenance and repair of heritage structure, as this is one of the upcoming area, and we can use this application of 3D printing, extended application of 3D printing in diverse areas other than the biomedical applications also. So this is another a promising area where a lot of attention from the manufacturing people is required. So in coming few minutes, I will be discussing about the modifications and the advancements that we are doing at our end for maintenance of such heritage structures. But just I want to have a brief of some of the basic things so that I can directly go to the application part. So as an overview of 3D printing, we all know this is a quite established process from last 3 decades. People are extensively using this. As a layman, if I talk about, I have some CAD file, I give it to some printer, and printer gives me some part, which is maybe a functional part, or it may be a non-functional part. Means I can directly use it for as a end user application, or it can be for demo purpose also, right? So as regard to the different technologies for 3D printing is concerned, the technologies may involve powder-based technology, it may involve polymer based technology, there are metal based technologies, and of course nowadays we are oftenly talking about the bioprinters also. We are interested in printing with biogels also, and there are a lot of studies where people have basically hybridized the polymer based technologies with metal based technologies and with bio based technologies also, like hybridizing different domains of materials and then clubbing it to make a some functional part. You can see here for the just demonstration purpose, I'm showing one technology which is called a Z-cast process. And here the powder is being sprinkled and some binder is there. So layer of powder and layer of binder is basically giving me the 3D part. So just for the demo purpose, I have a loose powder. Some roller is, making it flat, and then there is a layer of powder and layer of binder. So I am getting some printed component, and finally I am baking it in some furnace. And based on the cavity I am creating, I am making this component to be used for as a some functional part through investment casting purpose or through the sand casting purpose. This is quite established thing, and I suppose around 30 years back this technology was into the market and it has been commercially well explored, right? Now this is the thing which is quite common when we talk about the use of 3D printing technologies for making some cast or for some molds. Now the little extension to this, let us talk about what is the 4D part we are interested. So as we all know, 4D printing is basically the printing of some smart material. This printing may involve some smartness because of the inherent properties of the material. We call it as intrinsic features or the extrinsic features, right? So intrinsic features mainly involves the internal property and extrinsic feature based on the external factor. Like for example, I have a PVDF material in the form of polymer, which can be used for some piezoelectric properties with the application of some voltage or with the application of some load. Like we have a piezo crystal, we are typically as a mechanical engineer, we are using it for some force measurement in dynamometers, which is based on the piezoelectric actuation base, right? So I am applying some load, some change in dimension is there. Again, release the load, it will come back to the original dimension. So there is a property of self inspection and contraction. Now we want to use this property in some 3D printed material for some smart applications, right? Similarly, some of the materials may not have this property, but we can add this property through some reinforcement. Like some polymer is maybe not having some conductivity, right? So we want to add some conducting property into this material. So I can put some metal powder like aluminum powder, copper powder, graphene powder, which can basically, after reinforcement, is giving me some desired property. Then there is another way of getting some smartness into the material is the use of the metamaterial structure. So typically in metamaterial, we are interested in kirigami, origami type structures, where we can have a maybe reduction in the weight of the component, right, for developing some smart end effectors for some surgical applications. So if you just take the case of the polymers only, the smart materials in case of polymers are categorized as shape memory, shape changing, and metamaterials. There have been a number of papers on one-way programming, two-way programming, and multi-stage programming. We can use all these different types of programming depending upon the applications we are interested. I will just explain in the coming slide. Like for example, my material is in state A. I give some stimulus. The stimulus can be in the form of light. It can be in the form of thermal effect. It can be in the form of some chemical reaction. It can be in the form of some mechanical loading. It is converting into state B, and then again give some other stimulus, it is coming to the state A. I give very common example to my students. In nature we see there are some flowers which open up once there is a there is a sunrise, and once there is a sunset these flowers are getting closed. So there is some stimulus which is basically controlling the mechanical movement, right? We have a very common example of sunflower which always faces towards the sun, and as there is a movement of the earth around the sun, it also changes some direction, right? So we are interested in some stimulus which can basically under the effect of that stimulus my material is behaving in a controlled manner. Important thing is how I am controlling the behavior of my material. So from some state A to state B, through some stimulus I am changing. Then with another stimulus I am changing from state B to state A in a controlled manner. So this is a way of the one way of the programming, right? We can have a two-way, like from state A to B. I am putting some stimulus on. Let us say for some material, the stimulus is voltage or it is the current, right? So I am changing some voltage with the effect of that voltage. Let us say in case of PVDF crystal, the material is changing from alpha phase to the beta phase. Then again, from by coming back to the lower one, it is again converting from beta phase to the alpha phase, right? So this is a two-way programming. Similarly, I can have a multi-stage programming like with some stimulus A to A1, then A1 to A2, and there can be the different stimulus. And stimulus can be more than one, right? So it can be in the form of mechanical load, it can be in the form of current, it can be in the form of light, it can be magnetic field, some chemical or thermal, or the combinations, right? I have seen some of the papers where people have talked about 9D materials. So basically they are working on more than one stimulus and the behavior is really controlled one to have some different type of the properties. So this is one of the really low cost technology that is called FDM, where we have actually tried to make some 4D components that I will explain. How this technology actually works, we have a feedstock filament that is fed into some chamber where I have a control for the heating, right? This is basically called the liquefier chamber. On the other side of the chamber, I have a nozzle, right? So let us say the input dia of the wire is 1.75. So once it is coming out of the other side through the mechanical motion, normally it varies from zero point 0.2, zero point 0.4, zero point 0.8, depending upon the commercial model I am working. So this thermoplastic wire, once it is coming on the other side of the nozzle, I can move it in XY direction using some G code, right? Similarly, in case of the conventional CNC machining, so I can print the material layer by layer. So as there is a one deposition of the layer, the table is going down. So I can have a 3D part in X, Y, and Z, right? So this is the one of the most common cost-effective technology, which is based upon the use of the thermoplastic. We have used this technology actually to add the 4D properties into the material specifically for the structural engineering applications. Now, this is the basic setup that is required. The first figure that is showing over here, this is basically a melt flow indexer. This is as per ASTM D1238 standard. Basically, I am interested in the rheology of the material. Let us say I'm working on some thermoplastic like ABS or PLA, right? So I am interested in understanding how much thin section I can produce with that particular material. So I have to ensure the rheology, right? So for rheology, I am interested in how much gram per 10 minute that material can flow. So in this particular setup, I have a cavity over here. I put some load. I have a temperature control. Under the effect of temperature and load, some material is coming in out of this barrel. Here I have a die, and how much gram in 10 minutes that material is coming. It is called the MFI of that material. So if MFI is more, that means I can produce thin section. If MFI is less, basically it cannot be used for thin section. I have to justify for the thick sections only. So this is one of the basic tool that we used in injection molding also. We try to use this for the 3D printing also, right? So this is the first stage. Whatever the material I am getting as a thermoplastic, whether it is a primary or secondary recycled, I am basically interested finally to understand how much thin section I can produce. So accordingly, that I want to correlate with my 3D printer settings so that there should not be any porosity or misalignment or some like we have it defects, surface defects. Basically, I want to control the surface defects, right? So first, I control the rheology. Based upon that, I know how much settings for the load and temperature I have to maintain. Then I go for putting this material on a twin screw extruder. This is a standard setup where I basically put the granules between the rotating co-rotating screws, and basically I am getting a feedstock filament out of it, right? So that feedstock filament I am basically feeding to the polymer printer that I have just shown, the FDM, and I am getting a 3D printed part. Now here the point is, throughout the world we have a lot of issues for managing the plastic solid waste, right? So this is a really a big issue because a lot of environmental problems that we are getting because of the known better way of recycling of the thermoplastic. So this idea that we are sharing with you, this can be one of the milestone for making some usability of this waste thermoplastic. So technically, if you see, the thermoplastics recycling is categorized into four types: primary, secondary, tertiary, and quaternary. So this is what I am trying to explain is under the secondary way of recycling. Just for the understanding purpose, primary recycling means I am using a mechanical way of recycling without any reinforcement. Secondary recycling means I am using a mechanical way of recycling with some reinforcement. Tertiary recycling is basically chemical assisted mechanical recycling, in which I am using some chemical. And quaternary recycling means I am using this as an energy recovery process, right? So here I am interested in secondary way of recycling, means I am doing some sort of a reinforcement, right? So first, whatever the material I am getting, I am using it as a primary source, and I am putting some reinforcement, making some feedstock filament through the twin screw extruder. That feedstock filament is being put into 3D printer, and I am able to print some functional and non-functional part. No, why we are interested in this? Actually, this was one of the project which I am working with my collaborator. We got some idea that at some place in maybe in Canada, where the temperature goes around -30 or -40, we need some cabins where I have to conserve the energy. I have to continuously provide the heat source, and to conserve that energy, basically we are using timber and wood, right? So with the depletion of resources, we are no more interested in cutting off the forest, right? So I am interested to use some alternative where I can basically recycle or reuse the wood dust in place of the virgin cutting of the trees and all these things. Number one. Second, we are interested in recycling of the polymers. In most of the houses or the office cabins, we are using PVC paneling. So once the luster of the PVC paneling is over, we just throw it, right? So it adds to the plastic solid waste. So we want to recycle. Third thing, we are interested in like some sort of a smart tiles which have a self-aligning property. So and the fourth is the polymer that I am using, it should be biocompatible in nature. It should not be, harmful for the human. So what actually we projected in this is, we are interested in printing a tile in which the outer layer, which is accessible to humans, it is made up of PLA, as it is biocompatible and it is having no any harm effect to the humans. The second layer just adjacent to the PLA layer is the PLA plus PVC to accommodate plastic solid waste, which is available in bulk from the waste from the various office cabins. The third layer consists of PLA plus wood dust, basically to act as a thermal insulator. And the lowest layer, the fourth layer, we are trying to use PLA as a reinforcement with Fe3O4, basically magnetite powder, to give it some magnetic property. So ultimately, I am interested in four materials. So I have the PLA granules, I have the PVC granules, I have the magnetite powder, and I have the wood dust. So these different reinforcement were put into the PLA. We prepared the different feedstock filament and we printed the tiles. Now the idea is, suppose you are interested in some particular shape of the structure, right? And you have some wire mesh. You just give small quantity of the magnetic field, right? So my tile is basically getting aligned, right? So you not need, you are not requiring any separate person to help you in fixing the tile. So it will be self sticking. Once it is sticking, then you can put some screw or fasteners that can be applied. So after a few days you are interested in some other design, again you just apply the magnetic field. So and the tiles will be still sticking, and then you can unscrew and can change the shape. Because of the presence of the wood dust, it is helping me as a insulator. So the I am not requiring actually the wood or timber. Similarly, the PVC recycling I am able to do. So these are some of the benefits of getting this right. Now how it is 4D? The 4D is basically the file is this tile is getting attractive field, attractive effect because of the effect of the magnetic field as a stimulus. So we try to find out where what proportion we should use. So we selected the different weight proportion of PLA, different weight proportion of PVC, different weight proportion of Fe3O4 and wood dust, and we did some DOE based upon some design of experiment. We try to find out how much quantity of magnetization, corrosivity, and retentivity will be there, and we try to correlate with some BH curves and some ANOVA analysis, statistical analysis based upon some SEM and EDS analysis. We came up with some optimized setting. What should be the composition of which material into this? Like for example, just to explain, the virgin PLA that I was using, it was having a melt flow index of 28 gram per 10 minutes. The PVC that I procured from the local market, it was of 25. Now, if I am adding 10%, 15%, 20%, 25%, there is a variation in the the melt flow index of the material. Similarly, with the different reinforcement and with the different multi blend, I am getting a wide range of rheological property. As a operator for my 3D printer, I must know that I am little uncomfortable if I have to always change the setting of my hardware and software. So I have to correlate this with the proportion of the reinforcement that we can actually do once we are playing with the composition part, right? So we played with the different level of the reinforcement and trying to find out what is the peak load this material can take. Peak elongation, break elongation, peak strength, break strength, then percentage elongation at peak, percentage elongation at break, then their young modulus of toughness. All these things we try to develop, and some stress strain curve, their hardness relations. These things we actually able to develop. Then we try to see the thermal stability of these tiles also, like from the room temperature to high temperature, let us say 200, then from 200 to room temperature. Similarly, in the like a hot zone, as well as up to -40 also. So we try to correlate how much energy it will be absorbing in the heating cycle, how much energy it will be releasing in the cooling cycle. Then again their magnetic properties, right? How much retentivity will be there if I switch off the magnetic field, for how long this tile will be going to stick over there, right? So now you just see this is a very simple application, but it has a lot of meaning because I am just using this as a self-aligned tiles, right? So which can be really helpful in increasing the production rate for some construction industry. And typically I am able to manage the productivity. We will be able to manage the plastic solid waste and of course the wood requirement in a big way. So this is how 4D printing is actually contributing. Now to put my point further, we have tried to see the similar thing with some other material, like we put some graphene reinforcement in ABS, right, for some sensing application, and to see what is the effect of thermal actuation or the magnetometric actuations. You can see in typical this DSC curve, with the reinforcement of graphene, like in ABS I am putting, with the reinforcement, as the graphene reinforcement is increasing, the energy capacity joule per unit gram is increasing. That means this is going to be more thermally stable. So we also try to correlate with the magnetic property, how much will be the corrosivity, how much will be the retentivity, because I am interested to use this as some sensor which can be actuated with the with the magnetic field, right? So similarly, in another case, we use PVDF with the reinforcement of barium titanate and graphene to give some piezoelectric property. Here we are interested to use the voltage as a stimulus, not as a magnetic field stimulus, but the voltage as a stimulus. So again, we use PVDF with graphene, with barium titanate, and then playing with different proportion, we try to find out what is the peak strength, what is the break strength, what is the modulus of toughness, then stress strain curve, their thermal analysis, whether it is thermally stable or not. And we try to find out D33. Basically, this is the 20 picocoulomb per Newton. This we got out of this, right? So this is the another important thing that we observed with the different reinforcement of the material. Now, specifically in another example, we use the ZNO as a reinforcement in PLA, and we try to find out their thermal, mechanical, morphological, and shape memory properties. Like I have already explained, we have the granules of PLA in which ZNO particles were reinforced. This is some extruding wire. Some feedstock filament is being prepared. Its thermal stability we are checking. Then with the different level of reinforcement of ZNO, we are trying to see how thermal stability is affecting. Then basically, actually, we print a component like U and we put it into the water at room temperature of 25 degrees Celsius, right? And then we remove that part after dipping it, let us say for 5 hours, and what we observe, this U becomes V, right? So there is a change in the outer edges of suppose it is a forkand type thing, so there is a change in the dimension. But once we put it for some time, again it has shown some recovery. Then we try to see the same effect at some different temperature, let us say 40 degrees Celsius temperature. You can see the recovery was more, around 99% recovery we are getting. Then we were little interested to see why this is happening. So we try to see this effect based upon the glass transition temperature of the material. So we try to see the effect on the weight as well as on the volume and the dimensional feature at some low temperature and at high temperature above TG. So if we are working near TG, what we observed, we can have a recovery up to 99%, sometimes in case of 99.9%. So this is in this particular example, what we observed, that these type of materials have a double effect, means they have two stimulus. One is the temperature and another is the moisture content. So hydrothermal effect was there, right? So we try to correlate this change in dimension with the porosity of the material. So what we observed, where we are getting better recovery, the porosity was less, so we try to correlate with the morphological part of that particular component, right? So now, based upon these basic observations, we apply it in a heritage structure. How? So you see, this is a one of the heritage structure built during the British period, something around 1902. Now, in this case, the heritage structure is something like this. Suppose this wall of the site is accessible to me, and this wall is not accessible to me. Suppose it has a crack like this. I can fill the material like epoxy. We have some multinational solution like Hilti based solutions are there, where we put some epoxy through some pressure and the crack is filled. Then there is another case when the entry of the crack is large, but on the other side the crack size is small. I can again fill the cavity. But there can be a third case when the crack size entry is small, but on the other side it is large and it may move in a irregular manner on the vertical upward or the vertical downward. So I need some smart material that once I entered into the cavity, it is of the smaller dimensions, but once it is inside the cavity, it is expanding and taking the shape of the cavity. So basically that is the 4D. We are interested in these type of smart materials through some different type of the actuations. So what I need is, I need a basically the CAD file of this cavity. So what we did is, we did the 3D scanning, laser scanning. So we know the volume of the component. Now I need a 3D smart thermoplastic material and then the assembly in this area, right? So these are some of the structures where we are working. These are all our British period structures. Upper one, this structure was built in the Mughal period, something in 1667, right? So these are some of the sites over which we are working. Here there is another important thing that I want to discuss. You see over here, this is a some arch based structure where the whole composite material is same, But as a typical mechanical engineer, we understand this portion is under the compressive loading, and the upper portion is there are more tensile properties are required. But we are using a single composite material. But if I want to have a some smart solution, self-healing solution, I can think of a reinforcement which can have a compressive property better on the lower section and the tensile property better at the upper section. To put our point, we try to explore some combination of the multi-material printing. So we selected three material, HIPS, ABS, and PLA, just for the demonstration purpose. The basic difference was they have a lot of difference in their MFI. Like HIPS has a MFI of 7.5, ABS MFI of 8.7, PLA MFI of 13.5. This is in gram per 10 minutes. Then there is a significant difference in their Young modulus, their glass transition temperature, peak load, peak strength. All properties were significantly different, right? So we try to print it on a open source FDF system by keeping some parameter constant like dia of the nozzle, dia of the filament, layer height, default printing setting, printing pattern rectilinear. So these parameters were kept constant. What actually we varied is in one of the case we put the lower layer of ABS, then in another case the lower layer of PLA, then in another case with the lower layer of HIPS, and we try to use some DOE to see what is the effect with some other parameter like infill percentage, printing speed like this. So you can see these are some of the tensile specimen as per ASTM D638 with the different topping of layer. And we try to see what is the effect. Of course, the thermal stability we also did like we in the previous case. And then we developed the stress strain curve. And using this, we also try to see their microstructure. Now you see here in this case, this is a single composite material of the ABS. So I can clearly see the staircase effect in the 3D printing, which is also commonly seen in PLA as well as in HIPS. But once I have a lower layer of ABS, then I put a layer of PLA over it. What I am observing, some globule of PLA is spilling out. Basically, the reason is the difference in the TG glass transition temperature of PLA and ABS. So if I am taking a lower layer of ABS, then putting a layer of PLA, this material is actually spilling out. Basically, this microstructure clearly justifies that if I put some component, print this some component at this setting, it must have the low mechanical properties. We can actually correlate with the stress strain curve. You can see in the curve one, I am getting a lowest, triangular area of triangle. So modulus of toughness will be less in this case. So basically, we try to correlate the microstructure with the mechanical property, right? And we can basically justify which material I should put in the lower one, which in the middle, and which in the top one. So similarly, we try to see this on pull out test, like which is a very common test in case of the civil engineering application, and we can actually print some structural material. So that the thing is, if I am interested in some arch based structure where you are interested lower side with the compressive and upper with the better tensile properties, you can think of the different combination to make it really smart, right? So this can be one of the application. Now the programming part that I want to discuss with you. Now this is the another application for the 4D printing, specifically in case of the heritage structure. Actually, what we observed, the heritage structure that are present in this region, they are using basically the limestone. So this limestone is basically a calcium carbonate, right? So if I use the debris of that particular site at my place, that will be really good for the maintenance. There are some standards as per the government regulation or the public authorities regulation. Like in typical in country like India, we classified it as grade 1 structure, grade 2 structure, grade 3 structures. Like grade 1 structures are which are of the international importance, like the Taj Mahal we are having. Then there are the grade 2 structures which are of the national importance, right? Then there are the grade 3 structures which are of the state importance, and that is basically explaining the how the culture was there at that some local area, right? So for the grade 1 and grade 2 structures, you cannot use the foreign material. This is the law, right? But for the grade 3 structure, you can think of some foreign material to you can have some epoxy based solution which can be there for a particular type of the structure. So depending upon the particular geographical location, the law of land, we have to be very careful while using those type of things. So this basic study that I am presenting to you, this is on the grade 3 structure. right? So what we observed is in these type of these structures we have a weathering effect, and one of the basic weathering effect is of the, it is something like this is we call as the carbonation. Basically the carbonic acid H2CO3 that is really contributing for the damage of these type of the structures. So what actually we proposed as a 4D material is we used a PVDF reinforced with CaCO3. CaCO3 6% by weight. Actually, we calculated based upon the rheological property, rheological establishment after a series of experiment, and we printed some smart strips, right? And what we did is we give the exposure of DMF, which is CH3 to NCH to this PVDF CaCO3 composite. And what we observed with the exposure of this particular chemical, there is a significant improvement in the surface finish, hardness, and there is a decrease in the porosity of the material, right? So basically I am improving the finish of the component, but I am interested in 4D on the other way. Once I give a exposure of the carbonic acid to this, I can basically reverse the process in a controlled way. So that is basically 4D. Let me show this with an example. Like for example, the for some setting I have the initial surface roughness of 109, right, microns. Then I give a exposure of DMF to this. So for, let us say, 10-second exposure is there, right? So then I put that particular sample for 30 minutes in some cool environment below 0 degree, right? So what I observed, there was a significant improvement in the RA. So this micron, which was 109, this was reduced to 99. So then I did the same exposure for another 10 seconds and put it in a cold chamber. This is a, of course, there is a already established process in which people are working on maximum 3 cycles, and it has been reported that beyond 3 cycles we are not getting good improvement in the surface finish. Similarly, we are getting the improvement in the porosity. We are getting the improvement in the surface hardness. Basically, what is happening is the whole surface is made up of peak and valleys. Once I give exposure of some chemical, the peak is getting dissolved and setting into the valleys, right? So after three consecutive exposures, we are not getting further any good results, right? So that is why most of the research papers that have been reported in past 1 decade, they have recommended to use it up to the 3 cycles. Then we reverse this, right? So we give a after, so this is a exposure of the DMF. Then in the second case, we give a exposure of the carbonic acid, right? So you see, we started with 109, and with the exposure on the radial side we get again 108. Similarly, the porosity, you can see it was 18, so we get a porosity of 17.88. So what I want to say is, in a typical, let us say I'm interested in some maintenance of the heritage structure, right? So I can control the strength, I can control the hardness, I can control the porosity with the some 3D printed part. And specifically for the grade 3 type of structure, by firstly printing it with 3D, fitting it into some circuit by either compressing with some stimulus, and then putting into the cavity. Then again, once it is in the cavity, you are giving another stimulus, so it is expanding. So this will be take the shape of the cavity. Now I am interested in its finish, its hardness, its accuracy, its porosity, that I can control. Similarly, once I have to remove it, I will just do the other way, and I can remove it and can do the maintenance number of times. So this is some of the brief things that we are doing at our place. I think that's the thing that I want to discuss with you. Now I'm open for any question, please.